A fast-moving baseball flies directly toward your head, and you instinctively flinch before you even realize what's happening. Your brain instantly processes incoming light, recognizes a spherical object, and calculates its trajectory. You don't have to consciously run the math. Millions of years of evolution handle it for you in a fraction of a second. A computer looking at that same baseball has no biological head start. It doesn't see a threat, or any motion, or even a ball. By default, it is entirely blind to the context of the world. Because human sight feels so effortless, we often overlook the core engineering problem. Computers possess no inherent way to extract meaning from visual data on their own. To a machine, a photograph is a rigid grid of millions of isolated colored dots called pixels. Isolating a single pixel reveals nothing about the larger picture. It is merely a specific numeric value corresponding to a precise shade of color. This created a strict, impassable technological wall. Early machines could perfectly store and transmit millions of these numerical values, but they had zero comprehension of the images those numbers represented. For artificial intelligence to act within our world, it first needed a mathematical bridge to translate those meaningless dots into physical objects. Computer vision is the branch of AI designed to bridge that gap, teaching machines to build intuition from raw pixels. The process begins by scanning the grid for points of high contrast. Wherever a cluster of dark pixels meets a cluster of light pixels, the algorithm detects an edge, drawing lines between the different colors. Once those isolated edges are found, the system scales up. It begins connecting them, searching for continuous boundaries that eventually close in on themselves to form distinct shapes. Finally, the algorithm correlates these clusters of geometry, assembling them into a complete wireframe that maps the physical features of an object. Artificial sight isn't biological seeing. Rather, it is the rapid mathematical assembly of microscopic parts into recognizable structures. But building a wireframe leads to a new problem. How does the computer know what real-world label to assign to the geometry it just assembled? The answer lies in the training phase. AI models are fed massive datasets containing thousands of images that have already been labeled by humans. By layering thousands of examples of an object, like a car, the system deduces the universal mathematical pattern associated with that specific category. When the trained AI is shown an entirely new photo, it checks its new wireframe against its historical training until it finds a statistical match it recognizes. Recognition is achieved not through intuition, but through the mastery of high-speed pattern matching. This mathematical mapping allows machines to navigate our physical reality. In agriculture, autonomous harvesters now patrol fields, identifying specific plant diseases from photographs, and navigating terrain without a human driver. You likely use this technology every day. Smartphone cameras use it to recognize faces for focus and to apply filters that improve image quality. In healthcare, these same algorithms analyze complex medical scans, helping doctors identify anomalies with a level of consistency that assists in critical diagnostics. Retailers and security firms use it to monitor inventory levels, observe customer behavior, and manage facial recognition surveillance. And in transport, self-driving cars rely on computer vision to detect traffic signals, road lanes, and the movement of unpredictable pedestrians. We have moved from the initial blindness of a single pixel to the modern reality of systems that can map and react to entire environments. By translating pixels into patterns, computer vision has shifted computers from blind calculators into observant systems that can finally make sense of the visual world around them.